In this chapter, we begin our study of fluid mechanics. First of all, let's define a fluid. A fluid is a substance that can flow and change its shape to conform to the shape of the container. Gases and liquids are considered fluids. An important property of fluids, and in fact of all matter, it's in fact a defining property of all matter, is density. Density is defined as rho, and that is our Greek symbol for density, equals m divided by v, mass divided by volume. A fluid exerts a force perpendicular to any surface it's in contact with, such as a container wall or a body immersed in the fluid. This is the force that you feel pressing on your legs when you dangle them in a swimming pool. This is called pressure. We define pressure as the normal force per unit area. So pressure at any point in a fluid equals the normal force exerted by the fluid on a small surface at that point divided by the area of the surface. The unit of pressure is the Pascal. The Pascal equals 1 Newton per meter squared. An important unit of pressure is the pressure that you feel when you're standing on the surface of Earth at sea level. This is called atmospheric pressure. 1 atmosphere is equal to 1.013 times 10 to the 5th pascals, or 14.7 psi, pounds per square inch. If the weight of the fluid can be ignored, the pressure in the fluid is the same throughout its volume. But often the fluid's weight is not negligible and the pressure variations are important. Atmospheric pressure is less at high altitudes than at sea altitudes, which is why airliner cabins need to be pressurized. When you dive into deep water, you can feel the increased pressure in your ears. The equation that shows that when Y increases, pressure decreases, that is, as we move upward in a fluid, the pressure decreases, as we expect it to, is as follows. The pressure differential between 2 points is equal to the negative density of the fluid times g, acceleration due to gravity, times the height differential of the 2 points. Finally, we'll use Pascal's Law to solve many physics problems. Pascal's Law states that pressure applied to an enclosed fluid is transmitted equally throughout and to the walls of the containing vessel. Absolute pressure and gauge pressure. If the pressure inside a car tire is equal to the atmospheric pressure, then the tire is going to be flat. The only reason the tire stays firm and inflated is because the pressure inside the tire is greater than the pressure outside the tire, which is atmospheric pressure. The total pressure is called the absolute pressure. This is the pressure of the tire inside plus that pressure, the additional atmospheric pressure. The pressure inside, or the differential between the atmospheric pressure and the total pressure, is called the gauge pressure. So the absolute pressure is the gauge pressure plus the atmospheric pressure. So therefore, if your tires are inflated to a pressure of 35 psi, which mine are, and the atmospheric pressure is 14.7 psi, the gauge pressure would be the 35 psi. The total pressure, the absolute pressure, is going to be equal to 35 psi plus 14.7 psi, or 49.7 psi.